Welcome back, Honors 317, Essentials for Life, Air and Water. And in this video, we're going to focus on watersheds and flooding and how we might do some calculations or just have an understanding of what factors play the greatest part in having a flood event occur. And it's not just rainfall, believe it or not. So on this cover slide, I actually show an image of a U.S. Army Corps of Engineers lake, where this is below the lake actually. This is a project area. This is the tailwater where they've been holding the water back, and then finally they were able to release water. Once the natural water courses all receded, they could then release the water they were storing, and they did this to prevent widespread flooding. So in a simplistic form, in order to know how much water to hold back or to prevent from flooding communities, we need to understand how runoff works. And in this example, I've got an image of the Silver Creek watershed all highlighted here in white. And you can see Richmond on the map. Berea is down here. Mount Vernon's way down here. Lexington's way up here. And just south of Richmond is the Taylor Fork watershed. Actually, parts of EKU are in this map. Alumni Coliseum, the football stadium, the Justice and Safety campus, all of that has water that flows into Taylor Fork, which makes up the back end of Will Green Lake, and it flows into, all of this is called Taylor Fork. Taylor Fork actually meets the Silver Creek, and all of this is the Silver Creek watershed. The pinnacles of Berea, they start and make up the beginning of the Silver Creek watershed. So in the event that you had 1.4 inches of rain fall on this watershed in an hour, would we expect a flood or not? And how would people predict it or know it? And years of observation would help us, but it's good to know what factors actually would cause it. So why is calculating runoff important? Well, obviously, we probably want to prevent flooding. What are some possible mathematical measurements of runoff? So runoff, it's a physical science measure, right? And runoff is kind of, you need to know the height of the water. You need to know the width that the water occupies in a stream. So the height or the depth and the width, okay? So that tells you the cross-sectional area. You also need to know the speed. So like miles per hour or meters per hour. So now we've got, that horizontal distance. So that's another component. And then we have the speed, the time. So we call that discharge, and it's a volume per unit time, like cubic feet per second or cubic meters per second. So it's a volume per unit time for runoff, also known as discharge. And what might you need to know in order to calculate the runoff other than just how much it rained and how big the area is? Not every drop of rain that hits this is going to run off. Actually, not all of it. So there's factors that happen in the watershed that might make things run off quicker. So you can probably think of a few of those factors. So what might make the water speed up? How hilly it is? How saturated the ground's been? What is on the ground? Is it all pavement? Is it all grass? Is it forest? Those are just some of the major factors. So the rational equation that they use in the United States for a simple and quick calculation is Q equals VA, where, well, we're not at the rational equation yet, my mistake. So this is our discharge equation. So Q equals the volume times the area. And to calculate this, you can use this huge formula. We're not going to use this huge formula for in here, but some people use Q equals CIA. The runoff coefficient times the precipitation intensity if measured in inches per hour, and the drainage area in acres. And here are some sample runoff coefficients. So this is kind of the major concept for you all to understand in this class, is what factors influence our runoff coefficient. So our runoff coefficient pertains to how much water will run off. So when rainfall falls onto a lawn, 5 to 35% of it runs off. That means 95% to 65% stays on the ground. So having a lawn is far better from a runoff perspective than having a lot of concrete and roofs. So concrete streets, asphalt streets, concrete parking lots, concrete driveways, blacktop driveways, those all contribute to greater amounts of runoff. Some companies have got really good at actually dealing with this. So they've got alternatives to traditional concrete. So I'm going to pull up an example for you to view. Okay, so as I pull up this example, you might want to tune your audio down because they're loud, and I can try to tune it down here, but it may not change it. So are you ready? All right. Okay, so in that video, you would have noticed that they actually got rid of all 4,000 gallons of that water, and they did it without that water running off. It all went down inside the pavement. So they call that permeable pavement or permeable asphalt, and many communities have looked to it to help solve their runoff problems. But as you can imagine, some of the pores get filled up inside of it. So that's an issue that they still have to continue to get better and better at figuring out. So, all right, moving on into the actual slides again. So I'm going to play from the current slide. So we know that an area that's got a lot of concrete and roofs will have a higher runoff coefficient. So you could theoretically, I'm not going to do this to you, but you could theoretically be able to calculate the runoff from a 1 inch per hour rainfall event, how much rainfall or how much runoff would we have from something like that. And the rational equation uses Q equals CIA, where we actually measure the rainfall intensity in inches per hour, and we measure the area in acres. But, only in the US do they do that. In Liberia and Myanmar, they might be more agreeable to it, but the rest of the world only uses metric units. So our units of feet and cubic feet and acres are not as valuable to them in these other parts of the world, like all of Europe, Australia, all of South America, almost all of Asia. They all value like meters, square kilometers, that kind of stuff. All right. When we measure precipitation, you can get precipitation measured in hydrographs or hydrographs. So which is the hydrograph? That's the one on the left. And this is a hydrograph. We measure gauge height in feet as a proxy for actual discharge. So as the height of the river goes up, it'll be wide and it'll be flowing. And it's a constant rate based upon how high that gauge is. So this is a proxy for cubic feet per second or cubic meters per second on our gauges. All right, you can actually view the U.S. Geologic Survey data and actually pull it up and see what the flow rates are right now in Kentucky. Simple Google search USGS water data. It'll give you this website, waterdata.usgs.gov. You can select your geographic region as Kentucky, tell it to go. As it goes, it's going to pull up a map, and that map will show us how Kentucky is doing as a state with regards to our current conditions if we click on it. And you can look and see around the state what's going on. So red means it's very, very low, lowest 10th percentile, meaning this is a very dry period of time. Green, 25th to 75th percentile, is kind of like what's normal. Blue is there's a lot of water and it's flowing fast. Now some of these points that you see are actually changed by how much water is flowing out of the dams. But we see many of our small streams in Kentucky are actually potentially flowing slower than usual. So I just picked on one. This particular one is the Little Sandy River at Grayson. It's below the dam at Grayson Lake. And it tells us how much it's rained there recently. And it tells us what the discharge is on the Big Sandy River, how fast the water's flowing on the Big Sandy River, and how deep it is. So that's our discharge, cubic feet per second, and you can see those values. So that's just a little bit of information on the actual, use of USGS water data. And people use it for whitewater rafting, they use it for fishing, they use it for other recreational activities, and because they might be concerned about water rising in their backyard. But they should always use like the National Weather Service and follow and listen to the emergency advisories as well. So, all right, I'm going to pause this. All right, we're back. And now, based upon those videos and slides that you've watched, you should be able to answer these questions. So, what are two examples of some ongoing or recent U.S. water crises? So one, we've got like the drought conditions that we've seen in the Southwest. We've got the Ogallala Aquifer problem. We've also got issues related to people's ability to pay for water service. What are some designated uses for Kentucky's surface waters? So you have to think of like warm water habitat, right? We also have recreation, both primary and secondary, and we also have like domestic water supply. You should be able to answer some of these other questions, and I'll probably just share these review questions with you, for you to potentially answer for quizzes or exams, but these should be pretty easy to do. And one of the slides asks you which one, in case we didn't cover it thorough enough, which one is the urban and which one is the rural hydrograph. So you could imagine, based upon how much pavement is on the ground in an urban area versus a rural area. So in an urban area, we have a lot of people and there's concrete everywhere and it rains. Water falls on the ground and flows off very fast, so you see this big spike. In a rural area, we have less runoff, more of it goes into the ground, and we actually have kind of this rise and fall, but it's much slower because it doesn't all run off as fast. But we also have longer ongoing amounts of water. This is almost like the quote flattening the curve you think of with regards to our epidemiologic models for the coronavirus. So very much a natural system versus an anthropogenic system, or a lot of anthro meaning human, genic meaning created by, genesis, so anthropogenic, and this is closer to more of a natural condition in our rural landscapes. All right, so that's all for the hydrology section for now. Next, we're going to get into more hydrology, but like how do we deal with flooding? So I'm going to stop the video here.